Okay, class, now that we have the sum and difference formulas defined for both the cosine and the sine, let's take a look at some applications for the sine. So they want the sine of 7 pi over 12, and we won't be able to find 7 pi over 12 on the unit circle to get our exact value. But if we break 7 pi over 12 down into a 4 pi over 12 plus a 3 pi over 12, well, that's the same thing as 7 pi over 12. And when I reduce these, we can see that 4 pi over 12 reduces to pi over 3, and 3 pi over 12 reduces to pi over 4. Okay, now pi over 3 and pi over 4 are on the unit circle, so we can apply the sum formula. So sine of pi over 3 plus pi over 4 according to our formula here, I want the sine of pi over 3 times the cosine of pi over 4. Add to that the cosine of pi over 3 times the sine of pi over 4. Okay, now consulting our unit circle, or if we've got these memorized at this point, we know that the sine of pi over 3 is going to be the square root of 3 over 2. And the cosine of pi over 4 is going to be the square root of 2 over 2. Okay, cosine of pi over 3 is going to be 1/2. And the sine of pi over 4 is the square root of 2 over 2. Okay, so this ends up being the square root of 6 over 4 plus the square root of 2 over 4. And again, I can factor out the 1/4 and write this as the square root of 6 plus the square root of 2. Okay, this is the exact value, and if we ever need to utilize it in a calculator, we can plug this in and round it off to as many digits as we need for our application. But we can always recreate it in full with this. Okay, in this example, we've got a different setup here. We're seeing the right-hand side of our difference formula for sines already expanded out. So we're going to take this in the other direction. So if I think of alpha as 80 degrees and beta as 20 degrees, I've got this piece, and I can move it into the left-hand side and write this as the sine of alpha minus beta. So this would be the sine of 80 minus 20 degrees. So they're asking for the sine of 60 degrees. We have that on our unit circle, square root of 3 over 2. Okay, so here's an example where we have to do a little bit of detective work based on what we know about trigonometry to this point. And so I've reintroduced the unit circle here to help illustrate this. So they're going to give us some clues. So one is that the sine of alpha is equal to 4/5, and that alpha lies between pi over 2 and pi. So alpha's angle is somewhere between pi over 2 and pi. So it puts us in the second quadrant, somewhere in there. And what do we know about that? We know that the sine of alpha is greater than 0, but the cosine has to be negative in that entire range. So let's go get a cosine here. And what I'm going to use here is the fact that the Pythagorean identity says the sine squared of alpha plus cosine squared of alpha equals 1. So I'm just going to plug in what they told us, that the sine of alpha is equal to 4/5. So I'm going to square 4/5 here. Okay, so there's my sine of alpha. I'm going to square it and then add, we don't know the cosine yet, but we know that if I square it, add it to the square of the sine of alpha, I get 1. Okay, so that's going to be 16 over 25 plus cosine squared alpha equals 1. So if I subtract 16 over 25 from both sides, I would get that the cosine squared of alpha is equal to, I'm going to write 1 as 25 over 25 minus the 16 over 25. If I subtract that from both sides, I know that the cosine squared of alpha is going to be 9 over 25. Okay, now that means that the cosine of alpha is equal either to the positive or the negative result of the square root of 9 over 25. So that's a positive or a negative result, 3 over 5. Now we know which one it is because of this. It told us where alpha lies, and that's where my cosines are negative. So I'm going to pick the negative result for my answer. So for part A here, we're going to take negative 3 over 5. Okay, looking at part B here, we have, they're asking us for cosine of beta. And if we look at the sine of beta, we see that it's negative 2 over the square root of 5, or if they rationalize the denominator, that would be the same as negative 2 times the square root of 5 over 5. We're going to go ahead and leave it alone here because I'm still going to use this very same Pythagorean identity. So I'm going to take the sine of beta and square it. So that's going to be negative 2 over the square root of 5 squared. So sine squared of beta plus cosine squared of beta equals 1. So if I square this, it becomes 4 over 5. All right, I'm going to subtract 4/5 from both sides. So the cosine squared of beta is equal to, let's write 1 as 5 over 5 minus 4 over 5. Okay, so that equals 1/5. Now that's the square of the cosine, so I have to take and use the square root property from good old algebra. The cosine of beta is equal to plus or minus a square root of 1/5. Okay, so that's 1 over a square root of 5, plus or minus. And I'm going to rationalize the denominator now, so I'm going to multiply the top and the bottom by square root of 5. And now we've got this properly represented as positive or negative square root of 5 over 5. And for this notion here that the angle lies between pi and 3 pi over 2 is telling us that we're in this territory in quadrant 3. And again, the cosines there are negative, so we're going to take the negative result. And so for our answer for B, we're going to say it's negative square root of 5 over 5. Okay, for parts C and D, I've cleaned up a little bit here. So we just need to remember that the cosine of alpha is negative 3/5, cosine of beta, negative square root of 5 over 5. And they already gave us the signs, so we can use any one of our formulas. And part C is asking us for the sum formula for cosines. Okay, so the cosine alpha plus beta is equal to cosine of alpha, which is negative 3/5, times the cosine of beta, which is negative square root of 5 over 5. And then remember, we subtract for the sum function, for the cosine, whereas we add as a sum function for the sine. So we're subtracting and we're taking the sine of alpha, which up here they told us was 4/5, And we're going to multiply that by the sine of beta. And they told us that was, I'm going to go ahead and use the rationalized version here. Negative 2 square root of 5 over 5. All right, so let's just simplify all this. I've got a negative times a negative, so that's going to be 3 times the square root of 5 over 25 minus, and that's going to be a negative times a negative as well because we're subtracting. So let's change that to plus 8 times the square root of 5, also over 25. Okay, so combine this together, we got 11 square root of 5 over 25. Part D, we're asked for the sine of alpha plus beta. Okay, so we're consulting some function for sines, and we're going to get sine of alpha times cosine of beta. So the sine of alpha is 4/5. The cosine of beta we calculated for part B. It's negative square root of 5 over 5. And then we add, this time, cosine of alpha, and that's going to be negative 3/5 times the sine of beta, and the sine of beta again is negative 2 square root of 5 over 5. Okay, simplifying this result, we've got a positive times a negative, so that's going to be a negative 4 radical 5 over 25. And this is going to be a negative times a negative, so we're adding a positive result of 6 radical 5, also over 25. So combining our like radicals here, we get 2 times the square root of 5 over 25. Okay, let's look at a little different type of a problem using the sum and difference formulas. So remember, establishing identities, we should be able to take one side and make it match the other. They're true for all values of the variable or the unknown. So in this case, we're starting with cosine alpha minus beta over sine alpha sine beta. And our goal is to show that it's the same as the cotangent alpha times the cotangent of beta plus 1. So what we're going to do is apply the difference formula for cosines. And if we remember, that's going to be cosine of alpha times cosine of beta Now, since it's cosines, it's plus sine alpha sine beta. And that's above sine alpha sine beta. Okay, so what I want to do now is just split this. Instead of combining with the common denominator, I'm going to split it out and create two terms with the common denominator. So I will take the cosine alpha, cosine beta above sine alpha sine beta. Plus sine alpha sine beta over the same thing, sine alpha sine beta. Okay, so that's where we're going to get our 1. But this, if we think about it, the cosine alpha over the sine alpha is the inverse of the tangent, or what we call the cotangent. So we're after the cotangent of alpha. And then the exact same thing is happening here with beta. They're multiplied together, so we're going to take that times the cotangent of beta. And then this is plus 1. Okay, so we've learned about the sum and difference formulas for the cosine, then the sine, and we derived them in the case of the cosine and the sine. We're not going to do that with the tangent. We're just going to go ahead and let them, I'm going to take it on faith here that the tangent of alpha plus beta is equal to the tangent of alpha plus the tangent of beta over 1 minus the product of their tangents. Okay, and then here's the rule for the difference formula for tangents. So what we need to do here is do another identity, and we want to plug this in and show that we can reduce it to the tangent of theta. So let's just plug in the one that applies here. I've got theta plus pi. So that's the sum formula. So I'm going to take the tangent of theta, add the tangent of pi, and we're going to put that over 1 minus tangent of theta times the tangent of pi. Okay, and so the tangent of pi, remember now that's y over x, and pi is all the way over here, and y is 0. So this is the tangent of theta plus 0. And this is 1 minus the tangent of theta times 0, because in both cases our tangent of pi is 0. So we end up with tangent of theta on top, 1 on bottom. So just tangent of theta, and we've got it. All right, let's take a look at another identity here that we're going to try anyway. So if I take the tangent of theta plus pi over 2, and I try and use this sum formula for tangent, I'm going to get tangent of theta plus tangent of pi over 2. And we can stop right here because this is undefined, right? Y over x would be 1 over 0 at that location. But if we take a look and we think of the tangent, remember that the tangent is equal to the sine. One of our identities for the tangent, theta is equal to sine theta over the cosine theta. So let's see what happens if we rewrite it that way. So this is equal to sine theta plus pi over 2 divided by the cosine theta plus pi over 2. So we're actually not going to use the tangent sum or difference. We're going to use one each of the sine and the cosine. Okay, so using the sum formula for sines, we're going to take the sine of theta times the cosine of pi over 2 plus cosine of theta times the sine of pi over 2. Okay, and that takes care of the numerator. And in the denominator, we're going to take cosine of theta times the cosine of pi over 2. And remember, this is minus the sine of theta times the sine of pi over 2. Okay. Cosine of pi over 2 is 0. So this term is gone. And that leaves us with the cosine of theta times the sine of pi over 2. And that's a 1. So this is cosine of theta times 1. Down on the bottom here, we're going to get cosine of theta times another 0. But we're going to subtract the sine of theta times the sine of pi over 2, which is again 1. So here we get a negative sine of theta And so what do we call the cosine over the sine? We call it the cotangent, and it's negative, so we can simplify that as the cotangent, and it's negative since that's the negative sign.